Now let's do some transformation problems involving dilation, reflection, and absolute value. So let's say we have the parent function f of x equals 2 to the x, and I've drawn this below and labeled the points. I've also drawn it on every other graph because often it's easier to draw the parent function first and then make the transformation using the points on the parent function. So here's the parent function. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 to the negative 1 is 1/2, or 0.5. So the first one we're going to do is a reflection. G of x equals f of negative x. So using our parent function, that would mean that g of x is equal to 2 to the negative x. That means we're just going to be changing all of our x coordinates to the opposite of what they were, because if I want to get 4 for y, then I would have to have x be negative 2, because the opposite of negative 2 is 2, and 2 squared is 4. So all of my x's are going to have to change signs. So instead of 2, 4, I'm going to have negative 2, 4. I'm going to put this in a different color. Negative 2, 4. Instead of 1, 2, I'm going to have negative 1, 2. 0, 1 would stay 0, 1 because the opposite of 0 is still 0. And negative 1.5 would become positive 1.5. So this is what the graph would look like. Now, some of you might think, oh, that's just another parent function. Isn't that f of x equals 1/2 to the x? Isn't that just a decreasing exponential function? Yes, it is, because 2 to the negative x is equal to 1/2 to the positive x. So they are the same function. I didn't write that very well. Let me try that again. 2 to the negative x is equal to 1/2 to the positive x. Because when you put a negative exponent on something, you just take the reciprocal of the base. In this case, 2 becomes 1/2, and change the exponent positive. So they are exactly the same function. Okay, next one. H of x equals f of 1/2 x. Once again, we're making a change to the x coordinate. We're multiplying it by 1/2. That means my x's are all going to have to be twice as big to get the same output for y as I did with just the original x. So for example, if I wanted to put in 2 and get 4, now in order to get 2 as my input, I'm going to have to make x equals 4. So now I'm going to have, instead of 2, 4, I'm going to have 4, 4. My x value has to become twice as big. So 2, 4 becomes 4, 4. 1, 2 becomes 2, 2, because my x coordinate has to be twice as big. 0, 1 stays 0, 1, because 1/2 times 0 is still 0. And negative 1 becomes negative 2, 1/2, instead of negative 1, 1/2. So what happens is we have a stretching of the graph. It's twice as far from the y-axis as it was before. So times a dilation times 2. Now I didn't actually write the equation. Let me do that. So h of x is equal to 2 to the 1/2 x power. So you can also double check that your points match that equation. So for example, if I put in 4 for x, I would have 2 to the 1/2 times 4, or 2 squared, which is 4. And so this becomes the new exponent. It replaces the x in the original function. Now let's look at number 3. Number 3, or part C, I've actually combined a reflection and a dilation by multiplying it by negative 2. So there's going to be, the graph is going to flip and stretch. I'm multiplying outside the function, so so this number is going to affect the y coordinate. So if I were to write this, I would write this as k of x is equal to negative 2 times 2 to the x. Okay, so negative 2 outside the function. Now, that is not the same as negative 4 to the x. Once again, using order of operations, the exponent has to come first, so I cannot multiply these two numbers together and then apply the exponent. The exponent has to be applied first, then multiply by -2. So this is the simplest way to write this. I can't write this in any other way. Now, what's going to happen is I'm going to find my y value, 2 to the x, and then multiply all the y values by -2. So instead of 2, 4, I'm going to have 2, -8. And I just realized that doesn't actually fit on here, but we can make it work. So we'll just extend this down here, and we'll have 6, -6, -7, and -8. So 2, -8 would be clear down here. And actually I like to do this in a different color, so let me change this to blue. And then I'd have 1, 2 would become 1, -4. So that would be here. And 0, 1 would become 0, -2, because I'm multiplying all my y values by -2. And -1.5 would become -1, -1, because 0.5 times -2 is -1. So the graph would still have an asymptote, but it flips and stretches times 2. So both a dilation and a reflection here. Okay, now let's look at an absolute value function. And I've done in this I've done two transformations also. I did a translation and then also an absolute value. So if f of x equals x squared, write the equation for g of x equals the absolute value of f of x minus x squared. Well, all I have to do is substitute x squared for f of x, and I've got the equation. So it'd be the absolute value of x squared minus 2. Then draw the graph. Tip. First draw the translation, then the absolute value. And actually, I'm going to draw the parent function first. So let's draw the parent function. This would go through the point 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. So you need to know the key points of the parent function first. Now the first translation is take f of x minus 2, which would take the entire graph and shift it down 2. So now my points would be at 0, -2. Instead of 1, 1, I'd be at 1, -1, and I'd be at -1, -1. Instead of 2, 4, I'm going to be going down 2, so I'd be at 2, 2, and -2, 2. So the entire graph doesn't change shape, it just shifts down 2. So we went down 2. Now I want to take the absolute value. So the absolute value only affects, the absolute value of the entire function only affects the y value. So basically I'm going to put in x, square it, subtract 2, find the y value, and then take the absolute value. So if y is already positive, nothing changes it. But if I have a negative y value, it's going to become positive. So the only part of the graph that is affected is the section where x is, or y is below the x-axis. That point, those points are going to reflect up, and the rest of the graph is going to stay where it is. So I'm going to just kind of estimate sort of where the graph crosses here. So it looks like I've got a point here and here on the x-axis that are going to stay the same at about 1.5 and -1.5. Those are probably not exact, but close enough. And then 2, 4, or 2, 2, and -2, 2. And so this part of the graph right here doesn't change. What does change now is the red part, of the part below the y-axis, reflects up above. So 0, -2 becomes 0, 2. 1, -1 becomes 1, 1. And -1, -1 becomes -1, +1. So the graph looks like this. So whenever you have an absolute value of a function, you will not find any points below the y-axis. The entire graph is above the y-axis. And the only part that changes is the part that was below the y-axis to start with.